So today is chapter 9, and we'll just get right to it. I updated the syllabus. I made an announcement about that just to reflect the whole spring break thing I had in there before. That should coincide with the Thanksgiving break, not spring break, obviously. But I just fixed it in case one of you guys look at it and say, what the heck's going on? Okay, so today we're doing some center of mass stuff, some momentum stuff. This is going to coincide with a couple of labs you're going to do. It has a little bit to do with the torque lab, only from the perspective of you're going to be looking at the center of mass. And it also has to do with the projectile motion lab. The second part, the first part you did was just the ball flying across the room. The second part that you would be doing would be the ball going into the basket. So there's some conversions there. We're doing some elastic collisions, etc., that kind of thing. And I'll get into this more as we go through the lecture here. Okay, so the first thing we're going to talk about is the center of mass. Center of mass is, again, something that we've simplified because that's what we do in physics. We simplify things. And we look at complex objects of different shapes and sizes, and we break them down into a single point, like a particle point, and that makes it much easier to deal with. So if you have any kind of complicated mass, some weird shape, I don't know, floating out in space, this thing has a center of mass somewhere. Obviously, I'm just kind of making this up for the picture, but it has this center of mass somewhere. So you don't want to deal with the complicated issues of this. You want to reduce it down to a single point, say all the mass is right here, and deal with it in that manner. So they're talking about a bat. So we're looking at the trajectory of the bat and its center of mass as it goes through the trajectory. So it just makes a parabola. So instead of looking at the bat and its kind of complicated motion as it spins around, you can just look at it as a single particle point through each point of its trajectory as it goes through. Okay, so they simplify center of mass down to COM. Some other textbooks use CM. You can just kind of get used to that. Oops. But again, the little star things are usually pretty important. Center of mass of a system of particles is the point that moves as though, one, all the system's mass were concentrated at a single point, and two, all external forces were applied there. And this is going to become important later on for identifying what's going on inside and outside of a system. So we're talking about for two particles separated by a distance d, you have some particle, and we'll just, for argument's sake, say the second particle's larger. And so the difference we're talking about here is that this is particle 1. This is particle 2. We're saying that the origin is at the center of this particle. And so we look at the distance across, and then we say this is some distance d. Depending on what you want to do for different types of problems is where you're going to use the differences between these two. The two particles, for an arbitrary choice, this is the difference. This is more for like a generalized situation. So we're going to say we have our x and y system, y-axis, x-axis, and then we have the same situation. We have a small particle and a larger particle. I have to sneeze. Same deal, particle 1, particle 2, and then you're going to have some distance from some place that you've specified as the origin. So we're going to say it's at the where the y-axis meets the x-axis. So x equals 0 at this point, right? And then we have some distance, and we'll call this x1 because this has it labeled as x1 over here instead of distance. And then you have some other distance, again, starting from the same point, coming over to particle 2. So then this is some distance x2. So this creates a coordinate system for a more generalized situation. This is dependent on this particle being here. This is not. So it depends on the situation and what you want to do. It could be easier for some situations and harder for others. You want to choose the easier path, of course, right? So yeah, this is basically the differences between the two. You get a little bit of variation between the math here. So you have just mass 2 here, and then you have the distance between them, and then for this one you have two distances and the masses between them. If you haven't figured out by now, the problems you're doing in all these book problems, you want to look at the information that you're given and then apply it to the correct equation. So if you don't know for right now which situation is easier when you approach a problem, it may just be easier to look at the information that was given to you. So if this is from some arbitrary point, then you're going to have two distances, right? You have more information here that might be easier. For this one, if you're only giving the distance between two particles or two things, say it could be a car and a person, two billiard balls, whatever. Again, they don't have to be point particles. Then it may be easier to use this situation. Okay, so this is basically, I think, what I just drew. So this is, one of the things they've added to this is the center of mass. So this is using a system where you've put the coordinate system right on that point particle right here, right? And then we've figured out where the center of mass is and the distance to the second particle. So the distance between them is here. As this particle moves, the center of mass will change also, right? So you have a big object here, a little tiny object here. The center of mass is here. As this gets closer, it's going to shift the center of mass towards the larger object. If you have something massive, say the sun versus Earth, then the center of mass barely changes, right, as the Earth gets closer, because the mass is so massive of the sun compared to the Earth. So you have the center of mass again here. This is the second situation where you have the generalized coordinate system, and you're figuring out the distances from some arbitrary point to both particles, right? So you have distance x1, you have distance x2. And all these are one-dimensional, right? So we're keeping everything simple. It's one-dimensional. And of course, so now this is just saying it doesn't really matter how many particles you have. You can continue to use this system to simplify things and to figure things out. So you got 72 particles. You can figure out the masses of each particle, the distance of them from something, and you can add them up under this summation symbol and figure the total mass out. Obviously, you're not going to be given a situation that complicated. That would just be extremely tedious, and you're not learning anything new. It's just kind of reinforcing the same thing over and over again. Again, this is one-dimensional, so even if you have something that's working in a three-dimensional space, you want to break it down into each individual dimension. That way it's easier to solve, less complicated. And then, of course, if one of these is the same, it makes it even easier. We'll talk about that in a minute here, I believe. So again, in terms of vectors, you can write it in terms of vectors. So you get the integration form, taking a limit of an infinite sum. And then, of course, again, coordinate by coordinate, we can write this. This is in the form of a changing mass, right? So you have the x, y, z position, and then you have the mass according to that linear portion in each direction. Okay, so uniform density, we have the density, typical mass divided by volume. You have the like derivative form of this. You have the derivative of mass over the changing volume, so the change of the mass over the change of the volume. Same deal. Breaking it down into individual components, x, y, and z. You have total volume being divided by the change in volume, and then you have the x portion in here for each one. So we can break it down by each linear component. Okay, so the center of mass lies at a point of symmetry. Symmetry makes things easier. Like I drew that kind of complicated object in the beginning that doesn't have symmetry, that makes it more difficult. When it does have symmetry, that makes it easier. The center of mass right here does not need to be on the object. It does not need to be touching the object. So the example they're giving is a donut, right? So the center of mass should be in the center of this thing. It's symmetrical. It's evenly uniform on both sides, so the center of mass must be in the center of it. There is no part of the mass in the center, however, right? So it doesn't have to actually touch the mass. So we have this checkpoint 1. The figure shows a uniform square plate from which 4 identical squares at the corners will be removed. So it's a square, it's even on X and Y, and then you have little squares here which represent a portion of the mass, and they're going to remove them one by one to see where the center of mass ends up. So A says, where's the center of mass played originally? Obviously it's in the center. All things symmetrical, it must be in the middle. B, square 1, and these are being removed, I believe, so if you remove square 1, it would move into this portion. If you have all 4 of them removed and then you add 1, it would be moved into this quadrant. This B, it's saying, I think they've mixed this up. This should be quarter 4. Because if you remove 1, then the mass must shift to this section. So for C, along the negative y-axis, it's saying squares 1 and 2. So yes, if you remove squares in 1 and 2, then it must shift downward. The center of mass must move this way. D, squares 1 and 3. So again, you've made a new point of symmetry. So then it must be at the center again. E is squares 1, 2, and 3. So then it must shift over here. And all 4 squares are removed. Again, you're at a point of symmetry. It must be back to the center. So I don't know what's going on with these quarter 3 and quarter 4 backwards, unless it's just mislabeled, but hopefully you get the point. The center of mass of Earth's atmosphere. Okay, so I'm just going to go through these one by one as you do test taking skills. So this should be fairly obvious if you can understand the point by now. If you don't, you can go through the possible answers and figure out which ones make sense and which ones don't. Basically, Earth's atmosphere, you have a sphere that is the Earth, and then you have Earth's atmosphere that is just another sphere that goes around that sphere. So if you have a sphere or a circle, because we're going to look at 2 dimensions, because I'm not trying to draw this in 3 dimensions, it must be at the center, right? So if you have another sphere outside that sphere, same deal. It must be at the center. So they're trying to confuse you a little bit by saying that there's, some distance between the Earth, the surface of the Earth, and the atmosphere. So it's saying a little less than halfway between the Earth's surface and the outer boundary of the atmosphere. So they're trying to average the 2 here between them. But that doesn't make sense unless you're looking at a very specific, small, finite section of, like a section of the Earth with the atmosphere above it. So this doesn't make any sense. Near the surface of the Earth, again, that would be like an asymmetrical point. It doesn't make sense. Near the outer boundary of the atmosphere, again, some weird non-symmetrical point, doesn't make sense. Near the center of the Earth, this is the only one that makes sense. And the Earth is not a perfect sphere, of course, but when you look at it on a whole, it's pretty close for approximate purposes. So it's close enough. That's why it says near the center of Earth and not exactly the center of the Earth, because it would be off slightly. And there we go. Okay, the center of mass of the system consisting of Earth, the Sun, and the planet Mars is. So I can't even remotely draw this to scale, but you're talking about something like the Sun. This will draw. versus like the Earth and then like Mars. Right, so this is an absurd portion, the discrepancy between masses of these three objects. This is essentially zero. Both these guys are essentially zero compared to this. This is just so incredibly massive. When we look at the total mass in the solar system, it's like, I think something like 99% of it is the sun. So everything else is irrelevant. Even Jupiter, which is so much more massive than the Earth, it's still inconsequential compared to the mass of the sun. So the center of the mass of the system consisting of Earth and the sun and the planet Mars is, if you know anything about this, basically it's going to be pretty much where the sun is, because these things are just specks of dust floating out there. Closer to the Earth? No. Closer to the sun? Yes. Closer to Mars? No, that would displace it out here. At the geometric center of the triangle formed by the three bodies. Whatever, you offset these somewhere so they're not perfectly in line. You make a triangle. Again, no. At the center of the line, no, this doesn't make sense. So you go down, it must be B. Has to be at where basically the sun is. Okay, moving into linear momentum. You have P, you have the mass and the velocity. So we have the momentum. This is just a very simple equation. Again, if you have these things, it makes it very easy. You plug them into the equation, you move on. This is an important point. Can only be changed by a net external force. So basically saying that, again, everything in physics is conserved. So linear momentum is also a thing that is conserved. The time rate of change of the momentum of a particle is equal to the net force acting on the particle and is in the direction of that force. So this becomes important too as we move on. So we can write Newton's second law, right? This is just your standard F equals ma equation that we learned a while ago. Only now it's written in the form of momentum. And none of you guys are physicists, at least in my lecture class. I know I'm posting this in the lab classes too. I don't know if there's any physics majors in there or not. But this is the more proper form that we as physicists write Newton's second law. We write it as basically the change in momentum over the change in time. The F equals ma is a very good approximation for most real world things. Everyday things we interact with, cars and planes and baseballs and footballs and whatever. This does not work on an atomic scale when you have F equals ma. You run into a lot of problems because you start dealing with these extremely small things moving at the speed of light, this kind of thing. It throws everything off. When you deal with the momentum, this is an exact form for all methods, but sometimes you don't have this information, so it becomes more difficult. So the sum, again, you can sum up the particles in the system. You have this large M here instead of a small m, but still center of mass. Again, the system of particles is equal to the total mass. Again, we take the time derivative like we just did earlier, and you can do it for a system of particles. It doesn't have to be for a single particle. Again, this external force on a system changes linear momentum. Without a net external force, total linear momentum of system particles cannot change. So again, this is similar as the last chapter where we have a system, and as long as everything stays within that system, everything's conserved inside it, right? When you start acting upon like the outside of the system, you start bringing in things from the outside, then you can start changing what's internally happening to that total system. Okay, if the total momentum of a system is changing, so just explain this, right? We know right off the bat what I just said before. If the total momentum of a system is changing, there must be some external force. Because again, the total momentum of a system has to be conserved because everything inside it has to be accounted for, right? This total amount of momentum, it has to remain a total amount of momentum the whole time. So in the terms of mass and velocity, If for whatever reason mass would increase, velocity must decrease proportionally, right? If velocity goes up, mass must go down. But it must remain the same. The total must remain the same. The only way you can change this is by some external force. So particles of the system must be exerting forces on each other. This is within the system, right? It doesn't matter what they're doing to each other, bouncing back and forth. Say it's like silly putty or something. A little bit of it hits one, changes some mass. A little bit hits the other. They combine together. Mass is doubled. But the velocity has to change proportionally. So if the mass doubles, the velocity must be cut in half. So this one can't be correct. The system must be under the influence of gravity. So again, this could be true. It just depends. So if the system is on a table, the force of gravity is being exerted on it, but that's not necessarily changing any velocities, and it's not changing any masses. So if you drop it from a high height, then sure, the velocity is going to change, right? So momentum changes. But so this is conditional. So must be is not true. It's conditional. The center of mass must have constant velocity. So again, if the center of mass has constant velocity, nothing's changing. The velocity is not changing, then the mass is not changing. So this doesn't even make sense. A net external force must be acting on the system. Here you go. So this is true in basically all situations, not situational like this one. None of the above. Obviously, you have at least one half true and one totally true, so this is not correct. So you end up with D. Okay, J symbolizes impulse. You guys as engineers will encounter impulse more than, say, physicists usually will. You guys use impulses a lot because engineers essentially are doing physics in a real-world sense. So, again, we're defining J as impulse, and then you have some force as a function of time, and taking everything in respect to time. Right, so this is a force for a set period of time. You can put a constant force on something. That's not necessarily what you use an impulse for, but this is the way it's defined. You can use it for multiple things. We'll get into it more here in a couple slides. Change of momentum during the collision, right? So we're saying that the change of momentum, the change in P here, is equal to the impulse. And then we're going to get a bunch of different rewritten versions of this. Again, trying to correspond your graphical portions of these things, because sometimes you're just going to get graphs when you do things. And graphs are an excellent way to analyze information, especially from experiments, which you guys will do eventually. Here you have a more complicated graph than, say, something that is a square. Right, this we can just use algebra to solve. This you need exact coordinates along the way, and then you can figure out the integral of it. But basically you just need the area under the curve. So if instead of looking at this guy and taking the integral of it, you can average the force on here, and then we can do it very simply and figure out the same answer that this would have given us. So again, depending on what information you have, one situation may be easier than the other. You may not always be able to do this situation, depending on what the problem is given to you. For a steady stream of n projectiles, so that's these guys. So this is n number of projectiles. And for argument's sake, we're going to say it is 7. So in this case, n equals 7. So n is generally the number of things, right? If you do a summation, you're going to have n equals something. N equals the amount of things in that summation. In this case, they have 7 drawn, so I'm just going with 7, but I think they were just going with an n unknown amount of projectiles hitting this thing. So they're just constantly hitting it. So you have some object here, some particles coming in, hitting it, moves a little bit, particle comes in, hits it, moves a little bit, particle comes in, hits it, moves a little bit, just constantly over and over and over. course, I'm moving this, but they've drawn these brackets on here showing you it's not moving, right? So they've locked it in place. So if you want to find the impulse, we can look at the number of particles that hit and the change in momentum. And then again, so here's a rewriting. So the reason that this is written in this manner is just to remind you that these come in different forms. So if you're like, I don't know, I get some number of particles in some mass in some problem. Oh no, I don't have J, I can't do this problem. Just remember that these things equal other things, right? This is a great way to actually solve problems, and you absolutely have to do this. So if you're given number of particles, you're given some mass, maybe you're given time or whatever, you can solve for velocity possibly, etc. You have the average force you would need, obviously. But these things are interchangeable, right? So you don't have mass and velocity, but it's just giving you straight up momentum. You have P. You don't have this thing, possibly you're just given an impulse that's over here. Just use these things interchangeably. And then they're giving a couple of, I guess, sort of unique situations. If the particle stops, you have the final velocity minus the initial velocity. If it stops, the final velocity must go to 0. That's what it's saying here. This must equal 0. Therefore, the change in velocity equals the negative initial velocity. If the particle bounced back with equal speed, that means these two things equal each other. Therefore, it must be two of them, right? So again, unique situations. It may get you to the place you need to be faster if you want to use these. The product of the number of particles and the mass is the total mass for however many collisions. So we're writing the change in mass because the mass is changing as you add projectiles each time. As this red ball hits the target, the mass of the target plus the red ball is added together. Now you have a second red ball that's hit this, so now you have basically two of these masses, 3, 4, etc., constantly adding to the target. Okay, a ball hits a wall and rebounds with the same speed as diagrammed below. The changes in the components of the momentum of the ball are. So again, we've looked at everything in one-dimensional at this point. This is a two-dimensional problem. It's moving in the x and the y. So again, you're going to have to break things up into x and y components, solve them individually. If we break this up into x and y, we're going x, we're going y. It's moving in some x form here. We break them in x and y here. We can see basically the x is the same for both of them, right? It's moving in the same direction, moving with the same magnitude. The y is moving with the same magnitude, is just simply switch directions. So changes in the components of the momentum are change in P, the momentum of x. We can see the change in momentum of x is what this is saying here in every single one. So change in momentum of x of all the possible choices. It hasn't changed at all. So it must be 0, right? So this is automatically out. This is automatically out. It must be one of these two. This is automatically out. Now we're limited to two choices. Must be equal to 0. And now you're looking at the change in y. So we're looking at the change in y. So you look at the change in y. So it goes from a negative direction to a positive direction. So the change in y must be greater than 0. So you end up with C. We'll do another one here. The direction of the impulse on a struck baseball. So you have some bat hitting some ball. We'll say, again, come on, little thing, work. You have some x and some y. So this is going outward in some direction. Depends on how fast the ball was thrown. This is clearly irrelevant. The direction of the impulse of the struck baseball. The baseball is struck even if the ball is on a tee, which means the velocity is 0. you're still going to get some impulse of this. So this one cannot be correct. B is in the direction of the ball's change in velocity. So this is, I don't see anything wrong with this. So that's a possibility. Is in the direction of the force of gravity. The force of gravity is then working downward. We're essentially working in the x direction, so this is irrelevant. Depends on how hard the ball is struck. Again, if it's struck with any amount of force at all, it's going to be moving in the x direction, so this is irrelevant. It's going to have some impulse. Impulse is a scalar and does not have a direction associated with it. This is just wrong. It has a force in it, so it's not a scalar, it's a vector. So this is also wrong. So this one, again, didn't have any problem with it, so it must be correct. And then it's B. So now we're going to get into the conservation. So I hinted at this like a little bit earlier. We're looking at the just the conservation of it. And again, I tried to point out the importance of this. No net external force acts on a system of particles. It must be conserved. So like that wording there is very important, and just get that ingrained in your brain, right? There's no external force, therefore you're not changing the linear momentum. The total system must be conserved. Again, conservation of linear momentum. Again, no net external force. So again, if you have opposing external forces and they cancel each other out, there's no net external force. That means it's also conserved. So don't take it to be just that there is an external force, therefore the momentum's not conserved, right? It has to be a net external force. And again, you need to look at this situationally between the linear components of x, y, and z individually. The internal forces can change you can change the momentum inside, but again, you're not changing the total conservation. The total inside the system must be conserved. This becomes a big thing. It's very easy to interchangeably use momentum and energy because they're so often so similar to each other. But don't get them mixed up. As we move later on, you will have to use both of them. Okay. A shell is launched from a cannon and explodes mid-air. So you have some cannon. Make a little wagon wheel here. We'll have some kind of Civil War cannon, I guess. You have some projectile that has moved outwards, and now it is exploding. I don't know if that's the best explosion animation there, but that's about the best I can do. Which of the following is correct after the explosion? Okay, so what has happened here is we've launched this ball into the air. The total system that we're looking at is now just the cannonball. It explodes in midair, so it didn't say that something was shot at it and exploded it and made it break into pieces or whatever. So the cannonball itself is exploding, so the explosion must come from internal gunpowder or whatever inside the cannonball. Since the explosion exerts external forces on the shell, the forces must be moving outward from an internal portion. So there's no, if this is the cannonball, there's no external force acting on the cannonball, right? We can establish that right away by looking at the situation. The forces must come from inside the system, right? So they're internal to this. There's no external forces. So the explosion exerts external forces. This must not be true, since the explosion exerts only internal. And if you notice, you look at the possibilities of the suggested answers here: internal, 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 internal. it must be one of these. So A is automatically out. Both its horizontal and vertical momenta are conserved. So when this breaks into particles and pieces, we have some pieces flying out in the x direction, right? These are both just going to be completely x, and some pieces flying out, yikes, in the y direction. So if you break it up into horizontal and vertical components, these must be not conserved in the y, because that's an external force. Gravity is an external force. But in the x direction, there is no external force, right? Because gravity doesn't work in the x direction. So both its horizontal and vertical momenta are conserved. This cannot be correct. Gravity is an external force. This is correct. Neither its horizontal momentum nor its vertical momentum is conserved. Again, it doesn't act in the horizontal, so this must not be correct. The explosion exerts only internal force on the shell, but the gravity is an external force. Same thing. Horizontal momenta is conserved. Vertical is not. So this is correct right here. And then the final one, vertical momenta is conserved. Horizontal is not. They just reversed the choices in case you weren't paying attention, right? So that's D. And the cat really, really wants attention. Okay, so we get into these two types of collisions. You have elastic and inelastic, right? These are the two types of collisions. For the elastic collision, again, this is important here. We're dealing with book problems and ideal situations, which are not real situations. In real collisions, some energy is always transferred, right? You always have some amount of heat, some amount of friction, some amount of sound coming out of it. These are all forms of energy loss. Depending on what it is, they may be very big or they may be very small. Depends on the material it's made out of, the amount of force, the material of what it's hitting, these types of things. So in elastic collisions, total kinetic energy is conserved, right? So we use this a lot. So basically, inelastic, some energy is transferred, right? And this is for completely inelastic collisions, this is the greatest loss of kinetic energy. This means that you have, again, two silly putty Play-Doh type things that are flying against towards each other. They hit each other and they combine to create one object. So you've lost the greatest amount of kinetic energy in this. It's completely inelastic. The objects stick together. One dimension. Inelastic collisions, again, you have things not being necessarily conserved. You have just basically mass 1, mass 2 have their own individual velocities, and you have, this is the initial portion, right? And this is the final portion. So completely inelastic, remember this meaning they stick together, is going to be this situation here, right? So in this situation, in order for these two bodies to collide, V1 must be greater than V2, meaning that this mass 2, is moving slower so that mass 1 can catch up to it. And so they're basically traveling like this. The mass behind is moving faster, so it's going to catch up to it. And they do not completely stick together. Basically, it's transferred some energy. You can see the magnitude of this, and it's probably hard to see. The length of this is longer than this, right? Once it hits, this is a billiard ball situation, meaning a pool table, right? Two pool tables, you have two balls traveling, one's moving much faster. It hits the second one, it transfers the energy. Now the second one is moving faster than the first one. We can see we've extended the magnitude of this vector. In the second situation, you have completely inelastic collisions. You have basically this thing is stationary. We've said that velocity equals 0. And then when this one hits it, basically just the velocities have become one. Mass 1 has stuck to mass 2. Now they're traveling together as a single mass. Center of mass velocity remains unchanged. So what we're saying here, and this is a pretty good figure that they're using over here. You have mass 1 over here. It's just the black particle right there. Is then approaching the I guess white particle over here, and they're figuring out where the center of mass currently is at this moment in time. So initially, the second mass, its velocity is 0, as indicated by here. Mass 1 has whatever velocity it starts with. So as it approaches, the center of mass moves. It gets closer to mass 2. And it gets closer here, and then right when it makes contact, there is a collision, right? So now the center of mass is perfectly on top of both of them. So now the two masses have become one mass, therefore the center of mass is in the middle of those two masses. It then, of course, mass 2 picks up a new velocity, and this is moving on. And then we just have the splitting of the momentums here, and how we can figure out the center of mass for the velocity, or velocity according to center of mass. Again, so now we have the elastic collisions where the total kinetic energy is conserved. Kinetic energy of each colliding body may change, meaning inside the system they may change and interact with each other, but the total kinetic energy of the system does not change. Again, must be conserved. And then they're doing again a generic setup. So here we have some large magnitude. This is similar to the situation we had earlier. The difference is 100% of the mass and velocity must be accounted for. So whatever direct velocity this has, it is exchanging that exact amount of velocity into this one, right? It loses a large portion of its velocity, but when you add these two vectors up, it should equal the original vector, right? So this becomes an easy situation where you are given certain information you can figure out and go back and find the missing information. And here we have it written out into just algebraic form, right? You have mass 1, velocity 1, initial, and then if you have something sitting still, the mass 2 is sitting still, that goes to 0, it's disappeared, right? We've simplified the equation because of that. Now again, like I said earlier, don't start mixing up momentum and energy, right? They're two independent things, and it's very important that we have both of them. Because sometimes we don't have enough information, and say you're missing two variables of one portion, you can use the information given to write two equations and then solve for the missing variables, right? So this gives you an additional equation that you may have to use, and it works in the same manner. Again, the velocity of the second particle is 0, therefore that information goes away, but normally it would also be mass 2 velocity 2 in both these parts. Same situation here. So just rewriting these things to solve for the velocities. You have the velocities, you can solve for each. Again, interchangeable, rearrangeable. Again, things I've already gone over, I think. So again, this is for a target that is also moving. So now instead of one starting at 0, now you have both of them moving again, so you can't zero out the original information, so it has to be added to the equation. Now they're heading towards each other, two different masses. It looks like the same velocity judging by the length of the vector, so you can do that information accordingly. This is a problem. You have a steel ball with some mass. It's fastened to a cord that is 53 centimeters long, right, like so, and fixed at the far end. So basically, it's just it's a bead on a wire type of thing, meaning that it's attached to both points. It must slide down that path exactly. It can't move outside of that. It's attached, however, and basically, it's going to collide with this block. If you try to do this problem at the bottom, the information you're given, you have some mass 1 here, right? And it's going to have some velocity 1. And this is going to have some mass 2 and some velocity 2. Right? So when you go to write this out as initial and final, when you do this, you're going to have m, if it keeps writing, oh, it's terrible, m1 v1 plus m2 v2 2 equals same thing, m1 v1 plus m2 v2. So and I don't want to write the subscripts because it's hard to write with this, but you have initial and final. So this is the entire initial portion, this is the entire final portion. Right off the bat, you can simplify the equation, right? Because you have mass 2, blip, goes to 0, goes away. Because this is not moving, right? So it must go to 0. After the situation, this thing collides with it. Obviously, it has to be moving. I believe it said it's on a frictionless surface, so we don't have to overcome any forces of friction. It must move. It's frictionless. Anything touches it at all, it's going to move it. So you got rid of this piece right here. Yay. When you go to solve for this, you're going to find that you're missing some of the information. And that's when you're going to have to go back and look at these two equations. So you're going to have to take the linear momentum and you're going to have to figure out the kinetic energy. So to do this, you need the velocity, right? So now we aren't, like usual, confining ourselves just with the equations we've learned in this chapter. You have to go back and use the things we've learned before. That's one of the things that people struggle with in physics. We move on each time, but you must remember the things that we learned before. It's all fundamental. It all builds upon itself. It's like a pyramid, right? That's why it's very important not to say, like, I don't really understand this part, I'm just going to ignore it and we'll move on and then maybe I'll never see it again or whatever. It's just not the case. This stuff all builds upon it every single time. So if you're blowing off this class and you're looking up answers to everything that you do in here, you are severely screwing yourself. Pandemic time's not going to last forever. You're not going to be able to Google everything that you're doing every single time for forever. So when you move on to future engineering classes, they're going to go, okay, you understand all this stuff. We're moving on. And some of you that didn't do the work are going to panic and say, oh my God, I don't know. I kind of swept this under the rug. I don't understand it. Don't do that. Make sure you understand all this stuff. So when you do this, you can just do your potential energy. You can do your MGH to solve for this. So you have the mass, the gravity, and the height. You can figure that out with how long this is and use your triangle. And then you can figure out the velocity using your potential energy, right? And then the second thing is, you'll have to figure out the speed of the block. So then you'd have to use your kinetic energy to solve for it. Okay, so there's a summary of stuff. We went over all this. Some of the stuff that I didn't go over specifically in the PowerPoint. Collisions in 2 dimensions. If that stops doing that. Apparently I've lost my pen. Collisions in 2 dimensions. This is the same as 1 dimension. We're just working in 2 dimensions. So there's not a whole lot of new information there. The typical fashion, you're going to get some angle in here. So you're just adding sine and cosine components to what you're doing. So it makes it more complicated because it's not strictly dealing in 1 dimension. You're dealing in 2 dimensions. But use the same forms that you did before. Anything that has an angle to it, you're going to break up into sine and cosine components. Do your x and y coordinate system. Split everything up in x and y, so it's 1 dimension just twice. And figure out things accordingly. The one other thing, and this is kind of specific situation, comes up sometimes, but they're saying this is a rocket equation. You have the variable mass, so the mass is changing. The way rockets work, it has a chemical propulsion, so it has like a certain amount of oxygen and hydrogen inside the rocket. We'll draw a little rocket here. It has some amount of, we'll say, hydrogen and oxygen, as it flies upward, um, it will burn the hydrogen, oxygen, the fuel mixture, whatever it has, and it expels it out the back. So as this gets higher, the amount of oxygen and hydrogen, to simplify what's inside it, gets smaller. Therefore, the rocket gets lighter. So that's what they mean by these masses are changing. And there's just some equations that go with this. So you have the mass times the acceleration, but the mass is changing. So you can use these equations to solve these things too. It shouldn't be that much different from what we've done before. So you can look at that on your own. Yeah. So if you have any questions, let me know.